there, guys. Welcome to Unit 8. We're going to be talking about the area underneath curves. When I'm talking about the area underneath a curve, we're trying to figure out equations based off of finding the most precise area. We know regular shapes like circles, triangles, rectangles, squares, so on and so forth. There are equations for these that we've already learned, like the area of circle is pi r squared, 1/2 times base times height. You have base times height, and you have side squared because it's a square and all sides are the same. Now, what we're going to be looking at are graphs and functions that we're going to be putting on the Cartesian plane, that we're going to try to find the area underneath that curve. And because it's irregular, we're going to have to use calculus in order to find its exact area per se. So let's go ahead and begin. So what I have here is a car is traveling so that its speed is never decreasing. Okay, so the speed here is showing that there are going to be velocities, or positive speeds, meaning it's always going to be, it's not going to be a negative. It's not saying that it's going to be in a negative direction and so on and so forth. But it says it's never decreasing over this 12-second interval. Okay, so the default when you're looking at a graph like this is to interpret the top as x and the bottom as y. Okay, so the top input is talking about 12 seconds, so time usually is the input. Okay, and it's from 0 to 12 seconds. The speed at various moments in time is listed in the table. So we're going to sketch a possible graph for this function, and then we're going to start looking at the area. Okay, so let's go to begin. So let's say we're going to do this by, let's say 3, 6, 9, 12, and 15. So we did by threes. And again, this was my input variable of x, you could say, which is talking about the time. And this is the y, which is talking about the speed. Okay, so we're just labeling this based off of what we're seeing from this table. And then we have from 30 all the way to 65. So let's go in increments of, let's say, 20. So here's 20. Here's 40. Actually, to make it a little bit more precise, I'm going to do increments of 10. 10, 20, 30, 40, 50, 60, and then 70 way up here. So 60, 70, 50, 40, 30, and so on and so forth. Okay, so what we're going to do is we're going to plot 0, 30 as a point. So we're going to go 0, 30, put a dot. Then we're going to go to 337, which is approximately here. Then so on and so forth. 645, 954, okay, 1265, which is about here. So whatever this graph looks like, it is a function. It does pass the vertical line test. We can say that the graph would possibly look something that could do something like this. Okay, and what we're looking at is just the interval from 0 to 12. So I'm not going to keep going on. I'm going to stop right at 12. All right. So when we're looking at estimating the distance traveled, okay, the distance traveled by the car, what it is we're estimating the area underneath this curve. Okay, because this is a speed, i.e. a velocity graph, this graph is plotting f prime of x. And what we're going to be doing from this unit on is doing the reverse process of the derivative. We know that the derivatives forward went something that looked like this. You know, you had the velocity, you had the acceleration, and then lastly you had the third derivative, which was the jerk. What we're going to do here is we're going to go backwards. Okay, so when we're given the third derivative, when we integrate or go backwards, we're going to end up having the second derivative, and so on and so forth. Let's say we're given the second derivative and we're going backwards, which the term is called integration. We'd get back to f prime of x, and so on and so forth. Okay, so f prime of x integrated would ultimately result in f of x. Okay, so we're going to get all these details and what this represents more clearly as we develop, but I'm kind of giving you like the heads up now of where we're going with this. Because this is a speed, otherwise somewhat like a velocity function, we're taking the area underneath the curve, which means we're integrating it. So we're taking one step back. We're not deriving forward, we're anti-deriving backwards. So that whatever that area is underneath the curve, and I'm going to shade that in gray, is going to represent, in this case, displacement. Okay? Displacement is that distance traveled. It's that final position minus the initial position. So there's a lot just thrown at you just now, but it's all conceptual in the fact of what is the area underneath the curve representing. Okay? So by the car in the 12 seconds, what we're going to do is, let me go ahead and draw this coming down all the way to 12. And essentially what we're trying to solve is this area right here. Okay? Now I'm trying to stay in lines as best as I can, but ultimately that's what we're talking about. We're talking about the exact area that's underneath with no errors that are coming off of the graph, just what's inside. Okay? Alright, so what we're going to use is, we are going to use rectangles. So rectangles ultimately will be the most precise and most accurate representation of what we're trying to do as far as approximate this area. And it's telling us to do finding the areas of 4 rectangles drawn at the heights of the left endpoints. This is called a left Riemann sum. Okay, so if you can see it right now, there's going to be 4 rectangles. Okay, so 4 rectangles are going to basically be placed into this graph so that we can try to approximate what the area is. Okay, and let's do the left endpoint. That means the left top tip of each rectangle is going to be hitting the actual graph. Okay, so when I draw these rectangles, it's going to look something like this. This left tip will go down, and will go up. And it's not drawn perfectly to scale, but what it is these rectangles are equidistant. Okay? Okay, so they all have the same width, if you will. Okay? So let's go ahead and label that right now. Each of these are going to have the same width. The width looks like it's a 3. Now they're not always going to be equal, but in this particular example, we're assuming that because it's only 4 rectangles, it has to be that we're assuming that it's going to be equal. They're going to be symmetric. They're going to be these 3 units for each one. Now again, they don't have to always be equal, but a big way that you can tell what the widths are is to look at the graph. And you can see the changes in x. You see that this first jump showed a change of 3, which is shown here. Another jump of 3. So all of these show a jump of 3. And that's a big way that we're going to identify what the bases of these rectangles are actually going to be. Okay? Alright, so what we're going to do is we're going to approximate what this area is. So let me go ahead and approximate this area real quick. I'm going to highlight it in orange. So this area for this first one is going to look something like the following. We need to look at this first rectangle, and we're going to try to determine, we know the base is 3. So area is equal to base times height. Otherwise, this base of 3 is going to multiply, this is very important, because it's a left Riemann sum, whatever this height is right here. Okay? So the way we're going to identify this height, because it's a left Riemann sum, is we're going to choose from one of these 2 heights. Okay? We can either choose the height of 30, which is going to be this one right here, or we can use the height of 37, which is going to be right here. Again, since we are using left Riemann sums, we will be using the height of 30. Okay? So this height of 30 is going to be what we're going to use as our height that we're looking for. So it'll be 3 times 30. So this area is going to be 90 square units, whatever it is. In this case, it's feet. So that first one is going to be 90 square feet. So we'll say 90 feet squared is the area of the first one. Okay? Now that you get the hint, or the gist of it, I'm going to go ahead and do all of these together in one shot. let's go ahead and keep in mind that our left Riemann sum is going to have this height, and this height right here, here, and here, that we will calculate the areas of all of those rectangles. Okay? Again, let me remind you, each of these bases show a width of 3, so that's not going to change. Okay? So let's go ahead and write this out. The first one was, again, 3 times 30. The second one will be 3 times something, 3 times something, and 3 times something. These all have a base of 3, so I can go ahead and write them all out just like that. And ultimately what we're trying to do is we're trying to add all of these areas together. Okay, so what was this height here? Okay, I'm going to get that height from what is the y value at 3. The y value at 3, and I will highlight this in green so you can see it stand out. The y value at 3 is going to show that it's 37. And then the left one at 6 is going to be 45, and you should start seeing it right now. And the left one at 9 is going to be 54. Okay? Notice when we're doing a left Riemann sum, if you wanted to visualize, this is how I would eventually like you to do after with practice, is to visualize these rectangles are going to be right here. Okay, so you see the jumps like we did before, the jumps of 3 are the bases. And then the heights will come from 30, 37, 45, and 54. If and only if it's left Riemann sum. If we were looking at a right Riemann sum, we would choose the furthest 4 right sides. And there we would use 37, 45, 54, and 65. And we're going to see what that looks like here in just a bit. But I want you to first see what this accumulation is going to be for part A. Okay, so looking at this, we have 3 times 30, 3 times 37. All of these are going to be added up together. And the way I want you to note this is you're going to do a Riemann sum, and it's going to be a left Riemann sum. So we're going to put L for left, and we're going to do sub 4 because there are 4 subintervals. Now, this is important. Again, I will remind you, not always will these jumps be perfectly equal. Sometimes it could be 3, 5, 10, back to 3. But for this case, because they are, I'm going to GCF a 3 out, and I'm going to worry about these 4 y values that I'm going to be putting in. And again, they're the left Riemann sums. Okay? So one more time, let me highlight. They're this, 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 and this. These y values are the y's that are going to be the 4 furthest left y values, which in this case are 30, whoops, let me do that in blue, 30, 37, 45, and 54. Okay, and if I put that into my calculator real quick, let's see what we get. Okay, so 3 times parentheses 30 plus, let's go back, 37, 45, 54. Okay, 37, 45, 54, and the answer is 498. So L sub 4 is going to be 498 feet squared. This is the area underneath the curve, okay? And because this area is the integral of this velocity graph, the way we're going to interpret is displacement. Again, I was showing you that here, that we go from the first derivative to basically the position function, but you're going to learn that that's called displacement. So that area, it was displaced on those 12 seconds. The distance traveled was 498 square feet. Okay? Or you could say, in this case, this is huge right now, what I'm about to say. We know area-wise, it should be feet squared. Okay? Like if you're looking at them like geometric shapes from geometry. But our units of measure were right here. They were feet per second. So when we're going to go backwards, okay, let me go ahead and show that right here. if you have feet per second squared and you integrate, okay, you find the area underneath the curve, your result units will become feet per second. But if you were given feet per second when you integrate, otherwise take that area underneath the curve, your accumulation is just going to be feet. So in this case, in the real world interpretation of this, the distance traveled was 498 feet. Now I know I've said a lot just on this first problem, but I'm going to be repeating this here and there as far as the big key items as I go through the rest of these problems. Let's go ahead and keep going. Alright, so we have, now this time we're going to look at a right Riemann sum. Okay, so we're looking at a right Riemann sum. In other words, if you were to draw, like I showed you on the last slide, 4 rectangles. This first one had a base of 3. Second one had a jump of 3, so its base is 3, and so on and so forth. So nothing has changed. They're still the same rectangles. The only difference now is that we're going to look at the 4 furthest y values, because those will say what our base times heights are going to be. Okay, so let's say right Riemann sum with 4. The first base times height, let me do all the bases first. Base 3 times some height, plus base 3 times another height, plus base 3 times the third height, and then plus 3 times the fourth height. Okay, again, because we're doing right Riemann sums, we're going to look at this first number being 37, 45, and visually you should start seeing it now. I'm going to pick up the pace a little bit, only because you know how the first one worked out, and now we're just going through the motions to show how the right Riemann sum would come out. Okay, so r sub 4 is equal to, you can do this if and only if they're equal distance as far as the width of the bases. So 37, 45, 54, and this is how I would prefer you to write it on your tests and quizzes and whatnot. 37, 45, 54, and 65. Okay, so again, we are taking the area underneath the curve, and we were looking at, let's say, we have 30, whoops, we have 3, 6, 9, 12, I'm just quickly resketching it, and then we had 10, 20, 30, 40, 50, 60, and just a quick sketch, just so you can see what it's looking like. 0, 30, 337, 645, 954, and last 1265. So there's the graph, and because we are doing right Riemann sums, that means the right tip of each of these rectangles is going to hit the graph. Okay, so here is the first rectangle, and you see that it's going to be over. It's going to be an over approximation. Just like this last one over here on the first slide was an under approximation because we had all this error that was still left over. Like all this was left over, we didn't account for. But again, we're just approximating area right now. This right Riemann sum is going to be an overestimation, and you see it above the graph. Okay. Let me go ahead and do the rest of these rectangles. So from the right tips of each of these rectangles, the right upper corner, if you will, this one is going to match with 45, this one's going to match with 54, and finally this one's going to match with 65. Okay, so you would write, let's go ahead and put this into our calculator real quick. Okay, so let me just go up, grab this, and then just change the numbers just real quick. I know that 37 is going to stay, but then the last one is going to be added. We're going to add that 60, I believe it was 65. Yeah, 65, and then we get an approximation of 603. So 603 feet were traveled. Okay, so again, the area underneath this curve that we're trying to get is just underneath, and all of this, just underneath the red graph, if you will, the function. Okay, that's our goal. Okay, so let me show that one more time. Here's the area that we're trying to get. And this time we were asked to do a right Riemann sum, which in this case is going to be an over approximation because of the fact that this is the area that we actually obtained. Okay, and you see already that it's an over approximation because these little corners, the upper left corners of each of these rectangles is showing an area of too much. Okay, all right, so that is the right Riemann sum. Let's now look at the midpoint Riemann sum. Okay, just real quick, I'm going to quickly go 3, 6, 9, and 12 just to get the graph. 230, 260, and then we have 030, 337, we have 645, 954, and 1265. Okay. Okay. So now we're going to do a midpoint. Okay. So these that you saw over here, I'll do them in black so that you can see them very predominantly. You saw that we were looking at the left Riemann sums. So we're looking at the left upper corners. The second slide we were looking at the right Riemann sum. So we were looking at the right corners of each one. And now for the midpoint, yep, you guessed it, we are going to, within a jump width of 3, try to see where this approximation of midpoint would lie. So you're seeing, like for this first rectangle, let me go ahead and shade it in orange, that where it touches the graph is not the left or the right corner, it's actually right in the middle. So I'm going to show you right here in the middle is where we touch the graph. Otherwise, the midpoint of that base. Okay? So between 0 and 3, okay, there's going to be a midpoint of 1.5. Okay, and of course the midpoint of anything is the average of something. That you could say the midpoint between 0 and 3 is just add them up and divide by 2. That's going to be 1.5. Okay? And then the midpoint of 3 and 6, again, you're just going to add them up. So you get 9, so it'd be 4.5. Otherwise, you can already identify it's going to have a jump of 1.5 to show that midpoint. Okay? So the midpoint does get a little bit confusing out of all 4. I'm going to show you the fourth one here in just a bit. But in my opinion, students struggle with the midpoint because they struggle to see that the base is still 3, okay, but that the y value is going to be collected from a at moment of 1.5, okay? So when I take 0, which is be right here, and 3, which would be right here, and when I add and divide by 2 and I get this average of 1.5, this that I'm about to draw is very, very important. This height, okay, this height right here, whatever I get from 1.5, that is going to be the midpoint, okay? That will be the midpoint height that we're going to get, okay? So just like before when we had base times height, this one we're looking for base times height, okay? And that's going to be the height for each of these rectangles. Okay, so whatever that height is, let's say that this is x and y, otherwise x and f of x. We're talking about I will get my first height, whatever f of 1.5 is equal to. And whatever f of 4.5 is equal to will give me my second height. Again, the midpoint between these two will be f of 7.5. So remember, this is saying a y value at 1.5. Okay? And I'm going to highlight it in green just real quick. The y value at 1.5 is right here. And in the graph, it would look like right here. Okay? And then so on and so forth. Alright, so it says, estimate the distance traveled by the car by finding the areas of 2 rectangles drawn at the heights of the midpoints. So this one's asking 2, okay? So I jumped the gun just a little bit. The other one's asked 4, but this one is asking just 2, okay? So my graph It's going to be a slightly altered, but the same concept definitely goes through. Okay, and the reason why we can only do 2 on this particular example is because of the fact we don't have a function. Because the way I was doing f of 1.5 all the way to f of 10.5, there's not a function that I can plug these into in order to get those y values. Unless we do a linear regression or quadratic regression, which is not what we do in calculus. Okay, we are not going to be doing that in that respect. The table that you're given should be all the information that you know. So when you see 2 rectangles, you need to go ahead and find, there's a jump from 0 to 12. So if I'm doing 2 rectangles, it looks like it's going to look like this. Okay? Where that base of the first one is going to be 6. And the base of the second rectangle is going to be also 6. And with the midpoint, okay, again, we are not having to do this because we don't have a function yet, but you would get this y value, which is very important for this area of the first rectangle. Let me go ahead and highlight that for you real quick. The base times height will yield the area, which is right here for this first rectangle. Okay? So let's go ahead and do that first rectangle. The area is 6 times what height? Okay, again, I have to show you what you will be doing if there was an equation. You would take 0 plus 6 divided by 2, which is 3, and this x value is where you're going to plug into the function, like f of 3 if you will, and whatever you get right here as an answer, whatever that number is, that is going to be your height for that rectangle. And in this case, we have 37. Because our value was 3, which of course, again, is that midpoint between 0 and 6, but the y value would be 37. Okay, so you have 37 for the first one. You have what looks like 54 for the next one. And the width is not 3. That's a common mistake. I'll put it in red. It's not 3, it's going to be 6. Okay? Make sure that you're well aware of that when you're working with midpoint Riemann sums. Okay? You did take the average to get 3, but from that your goal was to get 37 for that height. All the while the jump is still 6. Okay? So this is going to be midpoint sub 2, and that will give us the area underneath the curve. Let's see what we get. We get 37 plus 54, so 6 times 37 plus 54, and you get 546. Okay. So m sub 2 is 546 feet has been traveled, and that's the approximation. Otherwise, the area underneath the curve. Let me show you what those look like real quick. So there's, hold up. The midpoint is going to occur at 3, so it's going to look like right here. Okay, and the midpoint is going to occur at 9, so it goes straight left and right from 9. And this area underneath the curve, let me do it in gray, just like I was doing with the other ones. This is what we're trying to find and approximate. Okay. But this is what we actually approximated. And you can see that there is a little bit of over approximation because the stubble is sticking out, but there's also an under approximation. Okay, so let me go ahead and let me show you like in red right here. This is the overage, and this is the underage. So the under approximation. And unless this is a line, a perfect straight line, those will cancel out each other. But in this case, that's not the case. It's not a perfect line, and we'll talk more about that as we go through. Okay, so just the thing that's shaded in orange is the approximation that we got. Okay, so it looks like it's a little bit closer to what it actually will be. And then finally, last but not least, we have the trapezoidal approximation, or the Riemann sum. Okay, so we have 3, 6, 9, 12. And there's a lot of strength in me drawing this out for you. 10, 20, 30, 40, 60, or 40, 50, 60. Because of the fact that whenever you start doing it, it's harder to visualize if all you've ever done is just the table. Okay? So a lot of people need the graph, and that's why I'm actually drawing this out. Okay, little review. The trapezoid has two bases that are parallel. And then it has this height right here. And the equation for the area of a trapezoid is base 1 plus base 2 divided by 2 times height. Okay? So if I were to take this, these bases, okay, this base here and this base here, and I were to divide by 2, it would give me something called the median. Okay? So if this top was 10, this was 14, that length of the median, okay, would be 12. We know that from geometry. And when I multiply it by this height, okay, by this height right here, it's going to essentially give me a nice pretty rectangle where this overage right here, let me highlight it in green, this overage would end up filling that gap perfectly because it's a trapezoid, and this little piece is a line right here. And I would have an area that I will shade in orange that would be right here. Okay, so that was a little recap review with the trapezoid's equations. Now, if I were to take this shape right here, and if I were to rotate it to where it looked like this height would now not be going up and down, but it would be going left and right. And the base 2 would move here, and the base 1 would still be there. Okay, so what I did was I just rotated it, if you will, like that. Okay? Alright, so now what this becomes is the area of each one is now going to be, because it's looking like a graph, this is y1. Whatever this height is right here is that y value. Whatever this height is y2. So we would have y1 plus y2 divided by 2 times the height. Okay? And the height is now going to be something called delta x. It's going to be the jump or the width, the change in x. Okay? So if I were to draw this out the way I was drawing the other ones from the table, okay, let's go ahead and do that real quick so that you can see what we're going to be doing. We have 0.30, we have 337, 645, 954, and 1265. Okay, so here's my graph. Same stuff, but now we're going to have two rectangles. Actually, let's do 4. We're going to change this up just a little bit. We're going to do 4 rectangles so that we have a better approximation, and we're going to do trapezoids. Okay, so just like I showed you here, I'm going to have 4 that have y1 and y2 that there's a straight line that gets drawn between them, and it'll look something like this. Okay, so this first one from here and here, this is y1, this is y2. I'm going to draw a straight line. Otherwise, that is this part right here on that arbitrary trapezoid that I was talking about, so that we have this approximation right here. Okay? So y1, let me highlight these as I go. Okay, so y1 is right here, and that's going to be 30. Is going to be added to y2, which in this case is 37. It's going to be divided by 2, and then it's going to be multiplied by the delta x. Okay? So the delta x on all of these, because I'm doing 4 subintervals, let me go ahead and do that trapezoid sub 4. The delta x is going to be 3. So let me do like I did before. and GCF out that 3. Okay? And now I'm going to do the area of the next one. So if you notice, this right here, this y1 plus y2 over 2 is right here. Otherwise, the height. Okay? So area is base times height. Remember the way we flipped it on its side? This height is this delta x per se. And what we're going to do is we have this base times height. My bad. This base is the delta x. And the height is that y value that we got. So averaging those two y values, otherwise averaging these two y values, we got 30 plus 37 divided by 2 times 3. Okay? Again, I GCF'd out this 3 so that you could just not have to worry about multiplying by 4 different times and then adding them up. Okay? So let's do the second one. So we have this y value. Okay, let me highlight this as I go. This y value here of 37 is going to be with this y value at 6 of 45. Okay, so we're going to take the average of those y values. Okay, that's going to be whatever this becomes. It's going to be like the median. So let's say this was 10, this was 14. This median would be 12, just like I showed you from before. Okay, so this height is what we just calculated down here. This average of y's is going to be this. That's that height value. And when I multiply it with 3, I'm going to get the area of that trapezoid. Okay, which in this case, let me go ahead and draw that trapezoid out. Straight line from here to here, straight down. That's my trapezoid. And when I multiply it, my area that I will get, it does have that median still filled to it, but it doesn't look like the midpoint formula, okay, where you had the straight line like this, where you had overage right here, and then you had underage or under approximation right there. This is still going to be drawn like a trapezoid to where that area will equal this, okay? And no, it doesn't pop out of the graph, just equation-wise, that's how you get that value of that area, okay? And then so on and so forth. The next two are going to be 45 plus 54 divided by 2, and then 54 plus 65 divided by 2. Okay? And the reason why this is taking a little bit long is because first, this is an introductory to area underneath the curve of what it represents. I've talked about how it converts units. I've talked about the interpretation of displacement as far as the distance traveled, because it's going from that velocity function f prime of x back to f of x. But now, once you start practicing these go pretty quickly. You just got to make sure that you understand the differences between all four, especially the difference between midpoint and trapezoidal. Okay, so let's go ahead and put that 3 times, because we chose to do 4. Okay, parentheses, and then we're going to have 4 fractions here. Let's do this first one. It's 30 and 37. Okay, so 30 plus 37 over 2. Okay, then we're going to do the next one, which in this case would be 37 and 45. 37 plus 45 over 2. And these are the average of the y's. Then 45 and 54. Whoops. And that's going to be divided by 2. Let's see if I can get this off. Okay. And then let's go plus control divide. Let's see, 54 and 65. So 54 plus 65 divided by 2. And this is now going to give us, control enter, 551. Let's go to 3 decimals. 550.5. So 550.5 feet. Now, believe it or not, this one is really close to what the actual thing is going to equal, okay? But again, I want to remind you, all these were approximations, and you have to know how to solve all of these all the different ways as far as left, right, midpoint, and trapezoidal. So we have 498 feet, that was under. We had 603, which was over. We had 546, and ultimately 550.5 most likely will be the closest. We're going to talk about when, where, and how the closest will look like in class when we do practice problems. Okay, so yes, continuing with the graph, straight line down, those areas, like if I asked you to tell me what this area was here, you would say it has a base of 3 multiplied by whatever this height is here, which in this case would be that y value there. Okay? And that area would be just this orange, nothing sticking out, that was in the boundaries of what you drew as a trapezoid. Okay, so all this area would be 550.5 feet. Alright, so now let's go on.